How'd you even get in here? This is a physics thing. What are you doing? Whew. We are on Reddit. We are not supposed to be. Let me see. Can we check? I saw your email. I'm gonna get it. I'm gonna get to it later. I'm gonna get there later. Wow. Fall. Point, sir. I don't know. I have to. No one's getting extra credit. I'm gonna check grades later. During your late work. I'll find a way for you to make up the lab. This video. Interesting. I'll give it a couple minutes before people walk in. Thank you for the 2 people who are watching my stream. Go hit that like and subscribe button. You know, it's basically the way I get income. I'll be having a meet during your period. Not today, you hear. Today's schedule was a bit wonky, so I just put up the lesson I was going to do. We'll probably do one next time. We'll have a meet on Thursday for sure, because we're practically done with the year. Let me open up my program. Which one is it? There we go. There we go. Wow, one watching. Okay, well, as people join, they'll join. I wanted to do these 2 problems. Physics in popular media. We're going to be looking at 2 examples. The first one is, of course, Wile E. Coyote. We're going to find out how far he falls using just information from a video. So let's watch the video. This section pulled out. Very far. Good morning, Anna. Okay, I'm gonna watch this part. So he's projectile motion. And he straight up stops right here, right? We know that's not the case, but we're gonna go with it. It's gonna make our calculation simple. We're just gonna deal with his drop here. So let's keep going. He falls and he falls and he falls and he falls. Hey, Jonathan. Ray Mezzi. We missed it. Okay. So he's up. So here's where we're gonna stop. He's hanging out here. We're traveling straight down, so we're not really looking at projectile. His initial velocity is 0. He's not moving. He's gonna fall some distance in some delta t. He's gonna have an acceleration. We're gonna assume he's on Earth. We're assuming he's on Earth. And we're gonna calculate some delta y. This is our x value. The only thing we needed to fill out in this this set of data is our time. So we're actually gonna end up timing this. So let's see. 3, 4, 5, 6 seconds? Is that it? We can do better than that. Stats for nerds. Okay, so I did some research outside of class. And it turns out this mystery text right here is the time. So if we go frame by frame, let's see. He starts falling at, oop, there we go. There it is. So he starts falling at time of 63 seconds and 90 milliseconds. A minute and 3 seconds in the video, right? This is in seconds, this is in milliseconds. Let's go frame by frame. Well, we can jump to the end. How's it going? We're going to stop. I'm going to go frame by frame and determine when does he actually hit the ground. Let's see. I guess it would be here, because that's when he makes a puff of smoke. So let's go with that. So time 1 is when he started falling. Time 2, 70.61 seconds. We have to subtract the 2. So our delta t is going to be t2 minus t1. 70.61 minus 63.90. Break out my calculator with my little pop socket. So 70.61 minus 63.90. So Wiley Coyote in this case falls for a total of 6.71 seconds. So this is no longer a question mark. We now know this value is 6.71 seconds. Hey Stephanie, do I get extra credit for watching this? No, you should be doing this because it's fun. We're gonna look at some other examples later. So here we have our 3 values, and we can calculate the 4th. So let's go ahead and get out of the video for a second. Look at the 4 equations. 4 equations, physics. Let's look these suckers up. Here we go. So we're going to be using this one. Alright, on the screen for us. Delta x is v initial times delta t plus 1/2 a delta t squared. Bring up the whiteboard. Whoops, let's look at the problem we're going to do later. Get rid of that ruler. Okay. So this is our equation. We're trying to calculate our delta y in this case. So delta y, our v initial was 0, so this whole term just drops out, and we get 1/2 a negative 9.8 meters per second squared times delta t 6.71 seconds squared. To run this calculation, 6.71 times 6.71 times 9.8 divided by 2, and we get an answer of, change the thickness of this line, bothers me, a delta y change of direction of negative 220.6 meters, which makes sense, right? We're going down, so our delta y is negative, meaning our canyon height. I sound hurt. I don't know what that means. I'm hurt. Only 3 people are watching between 2 classes. So our cliff height. Where are my coyotes? gravity was 220 meters approximately. So let's look at the context of this though. Oops, put that away. See how tall, how deep is the Grand Canyon? Okay, so Grand Canyon is like 6,000 meters, 6,000 feet. Floor elevation 800 meters. So, having a cliff of 220 meters isn't like the worst thing in the world. Let's do a quick conversion. Let's do some quick math. 220 meters to feet. That is a canyon drop of 721 feet. 721 feet. Let's compare it to some things. Let's see, Eiffel Tower. Eiffel Tower is about 906 feet, so maybe a little smaller than the Eiffel Tower. That's not bad, right? That's not bad. Temporary close, bummer guys. So in this particular case, he dropped about 721 feet. That's a huge cannon, but not outside of the realm of possibility. Good for Wiley. Let's go. That was even longer. This will be more complicated. Ooh, okay. We're not talking about that. All right, let's do another example. I have two queued up. We may do more later. I wanted to do an anime, but I couldn't find a good scene. I'm still looking. You hear? Stop learning. Stop. You're not supposed to learn physics yet. Let's do this scene. Do I have it queued up? Queue that up. Oops, I want to lose that. Queue up on YouTube. It's giving me you from YouTube. YouTube. So let's watch this scene. Let's watch this scene together.
Opening launch bay doors.
Oh my god, it's 5 minutes. This is my favorite movie. It's called Gru and the Minions. For context, so Gru is an evil supervillain, and he's trying to steal the moon with a shrink ray. It's a huge... Woo! This is a strange movie. Alright, let's skip ahead. Okay. There he goes. So we're going to try to shrink the moon so he can seal it, which, for the record, would cause a catastrophe of ecological disasters, but we'll go with it. True that. It's the best score. It's worth it. Boo.
I've got it! I've got the moon! I've got the moon!
Okay, hold up though. Here's the moon. What do we know about momentum? what do we know about momentum? If we take an object and we make it smaller, it's going to retain speed. It's going to go up in speed, in fact. If we take the moon, a spinning object, and make it smaller, well, what's going to happen? Well, we can look at ice skater momentum. So we can see what happens when we make things smaller. Oops.
Skilled
Oh,
athletes
wow.
learn to understand and use angular momentum to become the best in their sport. Angular momentum is the product of a skater's moment of inertia and angular velocity and is represented by the letter L. When the skater is rotating with no net external torque acting on her, angular momentum is conserved. With her arms and leg outward, she increases her moment of inertia, which reduces her angular velocity. As she pulls her arms and leg inward, she is able to spin
Whoa.
faster since her angular velocity increases while her moment of inertia decreases. And this is how skaters become champions.
So she goes faster when she pulls her arms in because she's decreasing the amount of mass around. The moon would do the same thing. We're taking all that mass and we're fitting it into this little itty bitty place, but conservation of angular momentum says we should start speeding up. Our I decreased, so our W must increase. So we're gonna work through these problems. We're gonna work through this one. Okay. Boop. Control A. Get rid of everything. So, where has the moon? Let's talk about that. Hi, Isa. Welcome to my stream. Make sure to like, comment, and subscribe, and hit that bell notification. Here's the moon. The moon has some angular momentum, and it's going to equal the angular momentum of the moon after. Before Gru shrinks it. Here's Gru doing his thing. Woo! Angular momentum is represented by IW. What is the moment of inertia of the moon? Well, let's look it up. Moment of inertia of the moon. Oh, there's a NASA fact sheet. Huh. I guess I should show you what I'm looking at. Earth-Moon comparisons. Moment of inertia. MR squared. That's cool. Let's see, moment of inertia. Oh, wait, mate, is that? Yeah, it's your favorite streamer watching now. Moment of inertia of a planet. Sphere. So it looks like the moment of inertia of a sphere is 2/5 mr squared. So in both situations, this is going to be 2/5 mr squared times W. Okay, if we're shrinking the moon, we have to assume something. We have to assume that our mass is constant, right? This is a shrinking ray. This isn't a mass destroying ray. So the mass is there. So the mass is going to be the same in both cases. Cancel on both sides. The 2/5 cancel out. And we're left with r squared times angular speed equals r squared times angular speed. The reason we don't cancel those out is because our radius here is different than our little bitty radius there. So those numbers are going to be different. those numbers are going to be different. Our next step, well, we have to get those numbers. So what's the radius of the moon? Radius of the moon. According to Google, the radius of the moon, oops, in meters. It's a lot of meters. All right, that works. Go back again. So the radius of the moon before we shrink it. Back. There you go. Is 1.7371 times 10 to the 6 meters, million meters squared, times the angular speed of the moon. What is the angular speed? So moon rotation. So the moon takes approximately, go back here, the moon takes 27 days to rotate once on its axis. So to go 2 pi around, it takes 27 days. Let's do a quick conversion. 2 pi over 27 days. In 1 day, we have 24 hours. In 1 hour, we have 60 minutes. And in 1 minute, we have 60 seconds. You know what? I think I'm just going to keep it in days. I think that'll just make my calculations easier. So 1.7371 times 10 to the 6 meters. 2 pi 27 days. Cool. So that's that side. This side though, we're calculating the angular speed, but we need a new radius. The moon shrunk, as we can see from the video, it's smaller. We have to figure out that radius. So we're gonna try to find that out with some comparison. So our picture says the moon is as big as Gru's hand. The moon's as big as Gru's hand. How big is Gru's hand? We can work with that. First, we have to find out how tall Gru is. So if you look it up on how tall is Gru, I found a source calling him 14 feet. I don't buy that. I don't buy that for a second. I think that's wrong. So this Lazo character, I don't think did it right. Go watch this video if you want. This one is refuting the claim. But I'm going to be using this image. This image is going to help me determine how tall Gru is. I come with a fancy ruler, so let's see. From the bottom, each of these segments is divided into 8. 1, 2, 3, 4, 5, 6, 7, 8 between each 2 big segments. Don't ask me why. It's a wonky ruler. But if this is 0, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm counting again. 1, 2, 3, 4, 5, 6, 7, 8, 9 segments. plus maybe 2 more. So 9 big segments. Each segment has 8 units. That's 72 plus 2 more. So GRU is 74 units tall. The Minion over here, let's go ahead and count the Minion. How tall is he on our little chart? 1, 2, 3, and maybe 1 more. So 3 times 8, 24 plus 1. So the Minion is 25 units. Let's find out how tall the Minion. Go back and check those comment sections. How tall is a Minion? According to animationsource.org, the Minion on average are 3.5 feet in height. It seems to be these varieties. These are just shorter ones. This one is saying about under 4 feet. So we'll go with 3.5 feet. So 25 units is about 3.5 feet. So how many units does 74? We can calculate that. I realize how close I was. 74 units. So 25 gives me 3.5 feet. Let's do this calculation. 74 times 3.5. Divide that by 25. And we get GRU is about 10.36 feet. Which I'm going to say makes sense. 10 feet is not 14 feet. He's also a freakishly tall man. So GRU's about 10 feet. I'll take that. Obviously, animation is a little strange, but he seems to be about 10 feet. So we'll go with that. Cool. GRU's 10 feet. I don't think this is a very good picture to use for his hands. So let's see if we can find another one that has a good picture of his hands in it. Remember, we need them extended. Let's see. We need a good picture of GRU. No, it's a toy. You know what? I think this one works. Copy image. So this relative size doesn't matter because we just need to calibrate our system. Okay. So how many tiles is this GRU? 1, 2, 3, 4, 5, 6, 7. Plus 1, 2, 3, 4, 5. 7 times 8 is, I want to say 40. 56, that's bad. 1, 2, 3, 4, 5, plus 5 more. 61 units tall. Alright, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. Okay. So 61 units is approximately, we said 10.36 feet. Now, without moving him, let's see if we can find out the size of this hand. I'm going to measure from the tip to about his foreleg. That should give us a good idea. There we go. this distance right here. Appears to be 1, 2, 3, 4, 5, 6, 7 units. So his hand is 7 units. If his hand is 7 units, and we know that 61 units, hey, it's Web, welcome to the stream. We know his hand is 61 units, if his whole body is 61 units, and that equates to 10.36 feet. Then we can do, once again, some quick maths. 7 times 10.36 divided by 61. And we get his hand to be about 1.18 feet. Which, you know, it's a big hand, for sure. That makes sense. Yeah, I guess we'll go with it. His hand's about as big as his head, and about 6 of them can stand on top. Sure, we'll go with it. So according to this, his hand is about that much. So if we go back to our source video, Don, what a coincidence. I see you. We go back to our source video, this moon must be approximately, however much we said. What did we say? It's okay, Luis. 1.1 feet. Thank you. Okay, so we've gotten that answer. Whoops. Based off the size would be 1.18 feet. 1.18. Let's get rid of this. I don't need a ruler anymore. And then we can go back to our initial calculations. Oh, 1.18 feet, 2 meters. So now we know that our R is 0.3, what was it, 6 meters. Now we can solve out our problem. I'll do it in my... Okay, so this is 1.7371 times 10 to the 6. And we're going to square that. And we're going to multiply it by 2 pi divided by 27 days. And then we're going to divide both those numbers by 0.36 squared. For context, here we are. So 1.7371 times 10 to the 6 squared multiplied by 2 times 2 pi, or 2 times pi over 27, divided by 0.36 squared. And here is our result. So we get a W equal to 5.41 times 10 to the 12 radians per 1 day. Remember, we left it in radians per day. That's already pretty fast. Let's convert that over to 1 day to seconds. I want to do the long conversion. every 1 day is 86400 seconds. So that's every second. It's turning 6.27 times 10 to the 7 radians. Per second. That's cool, but I also want to factor out a 2 pi. So we can get so the reason we're dividing by 2 pi is because I want to know how many times it's actually going around in revolutions per second. So 8.6 times 10 to the 11 revolutions per second. Reduced by 2 pi on the bottom, 1 revolution. Well, hello. Man, is my audio that scratchy? I'm gonna have to go back and see. Okay, anyways. Maybe it's just me. So we've run through our calculations. If Gru were to shrink the moon to the size of his hand, I am so sorry. This is gonna suck. Wait, I can actually go back and listen here. Let me open up my Minion. Ooh, it does sound bad. That much. So if we go back to our source video, it's probably because I'm streaming. I need to get a new mic. Anyways, we have our answer though. If Gru were to shrink the moon to the size of his hand, then via conservation of angular momentum, it would be spinning 8.6 times 10 to the 11 revolutions per second. That's crazy fast. He would not be able to touch it. That's a lot of revolutions per second. Oof. So I have, yeah, right, F in the chat. I have proved without a doubt that Despicable Me is impossible to do in real life because of this conservation of angular momentum concept. If we shrink the moon, it's going to spin because we're putting the mass in closer. That equivalence is going to be 8.6 times 10 to the 11 revolutions per second. That's pretty. That's pretty darn fast. Oop, I got a message. Okay. I think that's enough for today. Like I said, I was potentially going to do one more. I was going to do an anime, but I want to find a really good scene. And you guys gave me some good things in the starter to look at, so I'm gonna look at those. But I hope you enjoyed this stream. I see 9 of us are watching. Go ahead and smash that like button for more content like this. Nancy, how did you even get in here? Hi, Nancy. Hope you enjoy. I apologize for the audio quality. I'm going to look into getting a better mic in the future. But here I am just signing off. Thank you, you're here. Oh, everyone smash that like button. I saw it go up really fast. Tune in next week, and we're going to do some more popular media. Like I said, I'm going to have an anime queued up. So we've done kinematics, and we've done conservation of angular momentum. Next time, we're going to be doing impulse momentum theorem and analyze that, and probably an energy problem. Cool. I hope you guys have a good rest of your day. I hope you're staying safe, staying healthy. Do the flash next time. I want to look into the flash. We'll see how much energy it really takes. How much friction. Ooh, that might be a good one. We'll see. Okay, guys. Have a good day. Peace out.